This is the second video on chapter 36, the extreme value, absolute extrema, and the extreme value theorem. In this video and the next, we're going to be looking at applications, in other words, word problems. These problems, the difficulty in them is going to be setting them up, just like with the related rate questions. There is one difference between these questions and the related rate questions, and I'll illustrate that in a moment. But our first example is, this is a very classical example from calculus. We want to maximize the area of a rectangle. And so we have a farmer has 1,600 yards of fence with which to enclose a rectangular area along an existing fence. So we do not have to build this side. We have to build the other two sides. Now, here's where these problems differ from the related rate questions. In these questions, we're trying to come up with one decision, and our function is going to give us the result of that one decision. So in this particular example, our decision is how wide should this field be? So we make that decision. That decision results in an area. That area is what we want to maximize. And so, like the related rate questions, when possible, draw a picture. Draw a picture and draw a well-labeled picture. So here we have the width of our field. We have 1,600 yards of fence. So we're going to use X to build this side. We're going to use X yards to build this side, X yards to build the other side. That leaves us with 1,600 minus 2X yards for the third side. Remember, we don't build the fourth. So we have to build three sides. The area of this field depends on this decision, X. So the area, well, it's the area of a rectangle, width times length. So we have X times 1,600 minus 2X, that's the area of the field. This is a parabola that opens downward. We could just find the vertex if we wanted to. Now, remember, the extreme value theorem says a continuous function on a closed interval has a max and it has a min. We need a closed interval. Now, our closed interval needs to represent everything we can do, but not necessarily everything that we will do or should do. So for example, we can make X 0. If we make X 0, well, our area is 0. That obviously isn't a maximum, but we can do that. We can also make X 800. If we make X 800, then we have 800 here, 800 here. That leaves us with nothing here. And so again, our area is 0. We can do that. We don't necessarily want to, but we can do that. So these represent possibilities, not necessarily optimal choices. But we need a closed interval. Except there's one example, example 292. We do not have a closed interval, but we use our local min as an absolute min for example 292. But here we have a closed interval, so we'll calculate the derivative right here. So here we simplify the function, then calculate the derivative, and we look for critical points. Our critical point is 400. So we test our function at the endpoints and the critical points. So a of 0 is 0, as we've already said. A of 800 is 0. That's not a maximum. A of 400 is 320,000. This is our maximum area, 320,000 square yards, and we get that by choosing X to be 400. Example 290. You might recognize this. Part of this problem, the volume part, was in an earlier assignment. So here we're going to cut a square out of the corner of a piece of cardboard, fold the cardboard up, and we want to maximize the volume. And so again, this comes down to one decision. What is that decision? What size square should be cut out of each corner? So we label that side length X. That's the decision we make. That decision has a result. One side, the length of one side will be 6 minus 2x. The length of the another side will be 8 minus 2x. So our volume is x times 8 minus 2x times 6 minus 2x. The interval is 0 to 3. We can choose 0, that just means we don't cut anything out and our volume is 0. And we can choose 3. If we choose 3, then this side, then 6 minus 2x is just going to be 0. And so again, our volume will be 0. Maybe not something we want to do, but something we're allowed to do. And because we're allowed to do it, we're going to have the interval go from 0 to 3. Remember, we want a continuous function on a closed interval. So, this is our volume, and it simplifies to this. Our volume, now I'm skipping some steps on the board. You'll have to look at your notes where this is just a polynomial. We take the derivative, factor the 4 out of the derivative, and so to find the critical numbers we want to solve, this quadratic equal to 0. We use the quadratic formula for that. X is 7 plus or minus square root of 13 divided by 3. The square root of 13 is greater than 3. So if we look at one of the solutions, x plus square root of 13 over 3, what happens? The square root of 13 is greater than 3 because the square root of 9 is 3. So we have 7 plus something greater than 3 is greater than 10, divided by something, or something greater than 10 divided by 3 is greater than 3. What is my point? My point is, of your two critical numbers, only this one is in the interval. So we test the endpoints, we get 0 as we knew we would, and we test the critical number. So b of 7 minus square root of 13 divided by 3 is approximately 24.26. That is our maximum volume. And we get that volume by choosing this number here, 7 minus square root of 13 divided by 3, to be our x.